students, today we are going to learn real numbers from grade 10. Now, rationals and irrational numbers we've already started in grade 9. Rational numbers are those numbers which can be written in P by Q form, and irrational numbers are those numbers which cannot be written in P by Q form, like square root of 2, square root of 3. Now, together the collection of rational and irrational numbers form a new collection that is called real numbers. So real numbers is the collection of both rational and irrational numbers. Now, real numbers are the numbers which include both rational and irrational. Rational numbers such as -2/5, -2, 0, 1, and so on. And irrational numbers such as square root of 3, pi, etc. They're all real numbers. So till now, we've studied that we have rational numbers which can be written in P by Q form and irrational numbers which cannot be written in P by Q form. Now together they form a new collection that's called real numbers. Now lemma, this terminology we'll be using. Lemma, it's a proven statement used for proving another statement. Like we have a theorem. In order to prove that theorem, we have another statement that has already been proved. We are going to use that statement to prove the theorem. So that's called lemma. It's a proven statement used for proving another statement. Now comes Euclid's division lemma. Given two positive integers a and b, there exist unique positive integers q and r, satisfying a equal to bq plus r, 0 less than equal to r less than b. Now this means, for example, if we have two numbers, let's say 2 and 9. We have two numbers, 2 and 9. Let's say I'm dividing 9 by 2. So this would be 4 here. We'll have 4 as the quotient here. 2 times 4 would be 8, and we'll be left with 1 as the remainder. Now in primary classes, we have already learned that dividend is equal to divisor into quotient plus remainder. So this is the dividend here. This is the divisor here. This is quotient, and this is remainder. So as I just told you, dividend is equal to divisor into quotient plus remainder. So 9 is equal to 2 into 4 plus 1. Now, as we've just discussed, a is equal to bq plus r. So this is of the same form. When we have two positive integers a and b, and we are dividing a by b, then we are going to get a quotient q, a remainder r, which can be written in the form of a is equal to bq plus r. That means dividend is equal to divisor into quotient plus remainder. And this remainder would be strictly less than the divisor. It is strictly less. It cannot be equal to the divisor. Also, the remainder can be 0. It can be 0. It can be less than the divisor. So this is Euclid's division lemma. I'm repeating the same again. So we have given two positive integers a and b. There exist unique positive integers q and r, satisfying a equal to bq plus r, where 0 less than equal to r less than b. So we have two numbers a and b. We are going to divide a by b. Then we'll get a quotient q, a remainder r, such that the dividend, that's a, the number which we are dividing, and the divisor b times quotient plus r, and the remainder would be either 0 or strictly less than the divisor. Now let us proceed further. An algorithm. Now let's talk about algorithm. An algorithm is a series of well-defined steps which gives a procedure for solving the type of a problem. So it's a series of steps, and the steps together, they make an algorithm by which we can solve a particular problem. Now let's talk about Euclid's division algorithm. Now Euclid's division algorithm, we need to obtain HCF of two positive integers. Let's say the positive integers are c and d, where c is strictly greater than d. Then how to go about it? The step 1 in this algorithm is we have to apply Euclid's division lemma to C and D so that we can find whole numbers Q and R such that C is equal to DQ plus R, 0 less than equal to R less than D. Which means if we have numbers C and D and C is strictly greater than R, we are going to divide C by D. And then we are going to get dividend is equal to divisor into quotient plus remainder. And the remainder would be strictly less than the divisor. Now in step 2, if R is 0, that means if the remainder is 0, then the divisor in the previous step, that's D, would be the HCF of C and D. And if the remainder is not equal to 0, then we are going to apply a division lemma to D and R. So we are going to repeat step 1 in that case. And we are going to continue this process till the remainder is 0. Now, the divisor at this stage, that means once the remainder becomes 0, in that last stage, the divisor would be the required HCF. So this is Euclid's division algorithm for obtaining HCF of two numbers. Now, please read the question. Use Euclid's division algorithm to find the HCF of 135 and 225. So here we have two numbers, 135 and 225. We are going to obtain the HCF of these two numbers. So as we can observe here, 225 is greater than 135. So we are going to divide 225 by 135. Now when we divide 225 by 135, this is going to go one time and we are going to get 135 here. And we'll be left with 90 as the remainder. So this, using the Euclid's division lemma, I can write dividend is equal to divisor into quotient plus remainder. Now we have remainder, that's 90. It's a non-zero number. So we'll again do the same step with 135 and 90. So the bigger number 135, I'll divide by the smaller one, that's 90. So 135 divided by 90, this will go one time and we'll be left with 90 here. And 45 would be the remainder in this case. So we will again write dividend is equal to divisor into quotient plus remainder. Now again, we have a non-zero remainder, that's 45. So we'll repeat this step. So we are going to divide 90 by 45 and this is going to go two times and we'll have 90 here. Finally, we have the remainder 0. So we will again write this as 90 is equal to 45 into 2 plus the remainder, that's 0 in this case. So divisor at this step where the remainder becomes 0 would be the HCF of the given numbers. So the HCF of 135 and 225 would be 45. All right. So after this, we'll proceed to the next one. Now, students, in the next question, we have to use Euclid's division algorithm to find the HCF of 867 and 255. So in this question also, we are going to divide the bigger number 867 by 255. And this is going to go 3 times. So we'll get 765 here and we'll be left with 102 as the remainder. So here we'll write dividend is equal to divisor into quotient plus remainder. Now the remainder is 102 and this is the divisor. Since we have a non-zero remainder, we are going to repeat the steps. So we'll divide 255 by 102. This will go 2 times and we'll get 204 here and we'll be left with 51 as the remainder. So we'll again write dividend is equal to divisor into quotient plus the remainder. Now we again have a non-zero remainder. So we'll divide 102 by 51. This will go 2 times and we'll be left with 102 here and 0 would be the remainder in this case. So we have dividend is equal to divisor into quotient plus remainder. Now in this step, the remainder is 0. So we are going to stop here. So the divisor at this step, the last step, would be the HCF. So HCF of 806. So HCF of 867 and 255 is 51. Now in the next question, we have to show that any odd positive integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. So let us take a as an odd positive integer, and let us take b as 4. So by Euclid's division lemma, we can say that a is equal to bq plus r, where 0 less than equal to r less than b. So where q and r are integers. So b we have taken as 4. So in place of b, I'm going to put 4 in the next step. So we have a is equal to 4q plus r, 0 less than equal to r less than 4. Now 0 less than equal to r less than 4 means that r can take the values 0, 1, 2 and 3. Please notice r is strictly less than 4. So r cannot take the value 4. Now we have 4 cases when r is 0, when r is 1, when r is 2 and when r is 3. So if I put r is equal to 0, I'm going to get a as 4q. In this case, 4 is an even number and q is any integer. So here 4q will become even. But we have taken a as an odd positive integer and we are getting 4q as even, which is same as a. So that's not possible. So we are going to rule out this possibility. So let's now take r is equal to 1. If r I'm going to put 1 here, I'm going to get a is equal to 4q plus 1. Now we know 4q is an even number and 1 is an odd number. So even plus odd will give us an odd number. So this case is possible since we have taken a as an odd positive integer. Now let us proceed. The next case is r is equal to 2. R is 2 here. If I put a is equal to 4q plus 2. So in place of r, I have put 2. So this 4q is even, 2 is also even. So we are going to get even plus even, that's an even number. So a would also be even. So this case is also not possible since we have taken a as an odd positive integer. We'll rule out this possibility. Now comes the last case where r is 3. So I'm going to put r is equal to 3 here. I'll get a is equal to 4q plus 3. So this 4q is even and we know 3 is an odd number. Even plus odd will give us odd. So in this case, it's possible since a we've taken as an odd positive integer and 4q plus 3 is also an odd number. So this case is also possible. Now we can see that any odd positive integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Now children, let us discuss fundamental theorem of arithmetic. Now this theorem says every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Now composite number are those numbers which are not prime numbers. Like prime numbers are those numbers which have only 2 factors, 1 and the number itself, and composite numbers are those numbers which have more than 2 factors. For example, if I take 4, it's a composite number. It has factor 1. It has factor number 4 itself. It also has another factor, that is 2. So here, every composite number we can factorize as product of primes. For example, we have taken 18. 18 we can factorize and we can write it as 3 times 3 times 2. So 18, it's a composite number. We have written it as product of prime numbers. It is also mentioned here, and this factorization is unique apart from the order in which the prime factors occur. So the prime factorization is unique. That means we can write 18 as product of 3, 3 and 2. We cannot write 18 as product of 2 and 5. That's not possible. We cannot write 18 as product of, let's say, 7 and 3. That is also not possible because 7 and 3 will not give you the product 18. 2 and 5 will also not give you the product 18. So this factorization is unique. We can write 18 as product of 3, 3 and 2. but we can rearrange the prime factors. We can write them in any order. Like we can write 18 as 2 into 3 into 3, or we can write 18 as 3 into 2 into 3. So by fundamental theorem of arithmetic, we have understood that every composite number we can write as product of prime numbers. The prime factorization is unique, but we can rearrange the factors here. The prime factors can be written in any order. Now, children, let us discuss the next question. Check whether 6 raised to the power n ends with digit 0 for any natural number n. Now, this means 6 raised to the power n we have taken here. N is given to be any natural number. We need to check that it ends with digit 0. That means we need to check that this number has 0 in the ones place. Now, for any number to end with digit 0, 10 should be the factor of that number. If 10 is factor of that number, then we can say 2 and 5 both must be factor of that particular number. Both of them should be the factor of that particular number. So we need to check whether 6 raised to the power n has prime factors 2 and 5 both. Now 6 we can write as 2 into 3. So this is 2 into 3 raised to the power n. This can also be written as 2 raised n into 3 raised n. Now we can observe here that the prime factors of 6 raised to the power n, we have 2 and 3. We have 2 here, but then we don't have 5. So in this case, we can say that 2 and 5, they're not both factors of 6 raised to the power n. So we cannot have 10 as a factor of 6 raised to the power n. So 6 raised to the power n cannot end with digit 0. It cannot have 0 in the ones place. Okay, children, let us proceed to the next step now. Now, please notice, for any two positive integers, a and b, HCF of a and b multiplied by LCM of a and b would be the product of a and b. I'm repeating this. HCF of two numbers multiplied by LCM of two numbers would be the product of those two numbers. For example, if I take 26 and 91, I can write 26 as 2 times 13 and 91 can be written as 7 into 13. So as we can see, 13 is the common factor here and it is the only common factor. So we can say HCF of 26 and 91 is 13. Now the LCM of these two numbers would be 2 into 7 into 13. That comes out to be 182. So let us check the LHS here. Let us check whether what is the value of HCF into LCM. So HCF into LCM is 13 into 182. That is 2366. And now let us take the product of these two numbers. The given numbers which we have 26 and 91. We are going to take product of these two. So we again have 2366. So then we can conclude HCF of the numbers 26 and 91 multiplied by LCM of the numbers 26 and 91 is same as the product of 26 and 90. Now this question is based on the same concept which we have started just now. Given that HCF of 306 and 657 is 9, you have to find the LCM of 306 and 657. So now we know HCF of two numbers multiplied by LCM of those two numbers is same as the product of the numbers. So we have the HCF of the numbers given to us as 9 here. So I'm going to replace this by 9. And LCM I don't know. So I'm going to just write LCM here. And I know this is same as the product of the numbers. The numbers we have as 306 and 657. So I'm going to write 306 times 657. Now we need to solve for the LCM here. I'm going to take 9 on the other side and this will get divided. So I'll get LCM is equal to 306 multiplied by 657 over 9. From here, we can cancel out this 306 and 9. So this will go one time and this is going to go 3 here and then we'll get 4. This is going to go 34 times. Now we have 34 into 657. Now the LCM is 34 into 657. That is 22,338. So the LCM here in this case is 22,338. Now let us discuss the next theorem. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. So let us take a prime number. Let's take 2 here. We are taking 2 as a prime number. And let's take A as any positive integer. So let us take A as 10. Here, as we can see, that 2 divides A square. If P divides A square, that means we know that 2 divides 10 square. That means we know that 2 divides 100. We know that 100 is divisible by 2. So according to this theorem, if P divides A square, then P divides A also. So we know 2 divides 100, that is square of 10. From this, we can conclude that 2 divides 10 also. So I'm repeating this. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. So I'm repeating the example. If we have a prime number 2, if 2 divides 10 square, that's 100, then 2 also divides 10. Now we'll be using this theorem to prove the next theorem. Please notice, square root of all the prime numbers, they're irrational numbers. For example, we have square root of 2. 2 is a prime number. So square root of 2 is an irrational number. Square root of 3 is an irrational number. Square root of 5 is also an irrational number. So square root of all the prime numbers, they're irrational numbers. Now this we'll be discussing in detail in the live class. Now let's talk about terminating decimals and non-terminating decimals. A terminating decimal is a decimal that has an end digit. It terminates. It ends somewhere. Now, it is a decimal which has finite number of digits or terms. And non-terminating decimals are the one that does not have an end term. It has an infinite number of terms. So the decimal expansion goes on forever. Terminating decimals are those numbers which come to an end after a few repetitions after decimal point. Like for example, we have 0.5, 2.456, 123.456. So these are all terminating decimal numbers. They're terminating somewhere. They're ending somewhere. And non-terminating decimals are those which keep on continuing after decimal point. So the decimal expansion goes on. It doesn't stop. So they are non-terminating decimals. Now students, we have done this in grade 9 also. We have 2 types of decimal expansions. Terminating decimal expansions. The decimal expansions which are terminating, those are rational numbers. That means they can be written in P by Q form. Now in non-terminating decimal expansions, we have 2 classifications. We have non-terminating repeating decimal expansions. That means after a certain stage, the decimal expansion repeats. That means after some time, the digits after the decimals, they keep on repeating themselves. Those are also rational numbers. That means they can be written in P by Q form. Now we have non-terminating, non-repeating decimal expansions. That means the digits after the decimal point, they're not repeating. They're occurring in any order. So those are irrational numbers. So I'm repeating this. Terminating decimal expansions, they're rational numbers. Non-terminating repeating decimal expansions, they are also rational numbers. Non-terminating, non-repeating, they are irrational numbers. Now we have a theorem. Let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised n, 5 raised m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. So let us take a rational number p by q. How we can figure out that the rational number has terminating decimal expansion or non-terminating decimal expansion. Now in the next theorem, we have let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised n, 5 raised m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. Now this means if we have a rational number that's written in p by q form, how we are going to decide whether the decimal expansion is terminating or non-terminating repeating. In this case, we are going to prime factorize the denominator q. If the denominator q has prime factors 2 or 5 or both and nothing else except that, then we can conclude that the prime factor, then we can conclude that x has a terminating decimal expansion. For example, we have a rational number 13 upon 3125. Then we can prime factorize 3125 as 5 into 5 into 5 into 5 into 5. So we are getting 5 times 5 here. 5 raised to the power 5 we are getting here. So here the prime factors of 3125, we have only 5. So as I just told you, that a rational number will have a terminating decimal expansion only when the prime factors of the denominator, that is q, would be either 2 or 5 or both and nothing else except that. So in this case, we can say that the prime factors of 3125, we have 5, only 5. We have 5 raised to the power 5. So this has a terminating decimal expansion. Now in the next theorem, we have x is equal to p by q. It's a rational number such that the prime factorization of q is not of the form 2 raised n, 5 raised n, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating repeating. Now this means for a rational number to have a non-terminating repeating decimal expansion, the prime factorization of q must not be of the form 2 raised n, 5 raised n. That means the prime factors of q can be 2, can be 5 or both, but there would be any number, anything apart from 2 or 5, like 7 we have, or 13 or 3. So if we are getting any other factor other than 2 or 5, even if we have 2 or 5, but we are getting something other than 2 or 5, then we can say that it has a non-terminating repeating decimal expansion. For example, we have 64 upon 455. 455 can be written as product of primes as 5, 7 and 13. So we have 5 here, but then we have something other than 2 or 5, that's 7 and 13. So in this case, the decimal expansion of 64 upon 455 is non-terminating repeating. Now students, today we have learned real numbers and we have learned the Euclid's division lemma of real numbers. That means if we have two numbers a and b, then we can write a as bq plus r, where 0 less than equal to r less than b. Also, we have learned how to use this Euclid's division lemma to find HCF of two numbers. We've also learned fundamental theorem of arithmetic, which says that any composite number can be expressed as product of prime numbers, and that prime factorization is unique, but then we can vary the order of the prime factors. We've also studied rational and irrational numbers, and we've also studied the decimal expansion of rational and irrational numbers. Thank you, students. I hope the concept is clear to you.